In this video, we want to set up the partial fraction decomposition for this rational expression. We're not going to solve for the constants because that'll be pretty tedious in this case, and all of the different scenarios are included in this example. I do want to look at a more basic example here that I did in a video earlier, and I'll link that video to this in the description. Just remind you that when you're going to do or work this type of problem, it needs to be in proper form. So the degree of the numerator has to be less than the degree of the denominator. That's satisfied here. Degree of the numerator is 2 because you have an x squared. Denominator, we have a x plus 2, x minus 1 squared. So you multiply that out, the highest degree of the x will be a 3. So that has degree 3. So it's satisfied. You don't want any common factors, so it has to be in lowest terms. This one is. And then x plus 2 is a linear factor that is not repeated. So you set it up this way. On the numerator, we'll have a constant a. Denominator, we have x plus 2. Now the second one is x minus 1 to the second. So that's a linear factor that's repeated. So the format is some constant b over x minus 1, some constant c over x minus 1 squared. If that were a third degree power of 3, then you'd have another expression over here, d over x minus 1 to the third. And then this is just setups you're going to have. You multiply through by the lowest common denominator, which is, of course, x plus 2, x minus 1 to the second. This is what you get here. So notice, just multiply through, and this is what you get. And then simplify x minus 1 squared, we get this. X plus 2 times x minus 1, we get this. And then here we just multiply by the c. And then we just collect the terms. You treat this as an identity. So the coefficient of the x squared on the right side is a plus b. On the left side it's 1, so you have to equate then. This is an identity. A plus b has to equal to coefficient over here on the left side, which is 1. That's how we get this equation. And then collecting terms here, we have minus 2a plus b plus c. Collecting all the terms with an x, we get this. Coefficient on the left side, x has a coefficient of 1. That's how we get this equation. And then all the terms that don't have an x come together. That's a minus 2b plus 2c. That's the constant. On the left side, there's no constant, so that's 0. That's how we get this equation. And then you solve this system, any method you want. Elimination, substitution, combination of methods. You get your constants. A equal to 2/9, b equal to 7/9, and c is equal to 2/3. Like I said, I'll link the video so you can, just in case you haven't worked this type of problem is usually included in an algebra class, a pre-calculus, and of course you apply this type of method in integration problems in calculus. So let's go to the setup here. Again, this is in proper form. Degree of the numerator is less than the degree of the denominator, obviously. And there are no common factors. It's just in lowest terms. That's what we want. So let's start with the first factor here. Sometimes you'll have to factor this out. Instead of x minus 3 squared, they might give you that as x squared minus 6x plus 9. You'd have to factor it out and so forth. But this is the form you wanted it when you're going to get down to the different steps. So let's start with the first case. Got x plus 1, first degree. That's a linear factor. Exponent is 1 that is not repeated. So you just put x plus 1 there. And on top then, it'll be a constant. You can use a, b, c, d, and so forth. Since we're going to have a lot of constants here, I'm going to use subscripts. So instead of a b, I'm just going to start with a1. a1, a2, a3, and so on. And that's it for that one. Now the second factor, I'm going to plus here. The second factor is x minus 3. That's linear, but notice it's squared. So that's, first case here was linear and not repeated. That was the first one. This one is linear and it's repeated. So the way it works is you put down x minus 3. The power on that is 1. And then the constant would be, like I said, you could have a, b, c, and so forth. I'm going to use subscripts, so that'd be a2. And because this one's repeated, the procedure is to put the x minus 3 again, and now it's squared. Plus, and on top it's first degree here, so then we want a constant on top, so this will be A3. Now, had this been an exponent of 3, then we'd have x minus 3 to the third, and then on top another constant. But in this case, it ends there. So now we have a plus. Notice I have x squared plus x plus 1. That's an irreducible quadratic. In other words, it doesn't factor into real numbers, coefficients. So we just write it out, x squared plus x plus 1. And because this is second degree, the numerator could be first degree or constant. So in this case, the form we write here is another constant, a, has to be different than a3. So that's a4. And because it could be first degree or lower, because that's a constant, you write it as a4x plus, and then this could be, say, another constant, a5. And then we have a plus here. Now notice, x squared plus 9 does not factor over the real numbers. So this one again is one that is an irreducible quadratic. That is, it doesn't factor over the real numbers. So what we do here, kind of like the first case over here, repeated linear factors. Same sort of thing here, except in this case it's a quadratic factor. We write the x squared plus 9. The next one will be x squared plus 9 again, but it'll be to the second power. This is the irreducible quadratic that's repeated. And then x squared plus 9 to the third. Now again, had this been a x squared plus 9 to the fourth, we'd have another expression. X squared plus 9 to the fourth power. And then this will be a plus here, and then we continue. The subscripts will be A1, A2, A3, A4, A5. So this one again will be similar to this one here. This will be then got A5, the next one will be A6. So it'll be x plus a constant, A7. And this is to the first power of the denominator. And then we continue. Next constant would be a sub 8. It'll be x plus a constant, a sub 9. And then we continue to the next one. So the next constant we would use, just to make sure that it's different, would be A10. This would be an x, and then it's plus. And then finally, the final constant here would be a sub 9. And this is a reason that you were told not to solve for the constants, because we have 1, 2, 3, all the way up to 9 constants. So you were to solve this using one of the methods for solving a type of problem like this. You'd have a system of 9 equations with 9 variables, or in this case the constants, A1, A2, 3, 4, 5, A6, A7, A sub 8, A sub 9, A sub 10, and A11. That would be very tedious to find the constants. Keep in mind though, as you solve these, it's possible that some of these would be zeros. Thanks for watching. We'll see you next time.